Welcome everyone. What we're going to be doing in this video is we're going to be looking at the organization of the electron cloud. There have been many different models of the atom that has been presented throughout the years. One model called the Niels-Bohr model or the Bohr model says that electrons travel in these definite paths known as orbits. According to Bohr, each orbit has a definite or fixed amount of energy. So the electrons are in what we call energy levels. The energy level closest to the nucleus would be the one that has the lowest amount of energy, and then as you get further from the nucleus, the energy increases. So this is kind of like a planetary model. What he basically says, think of the nucleus as the center, and then an orbit would be a definite path where the electron, being negatively charged, travels. Okay, that would be one orbit. This would be perhaps a second orbit, a second energy level. And if you look, it's kind of like resembles like the planets going around the sun. So the Bohr model, as you can see here, there you could see N is equal to the energy level. So you got the first energy level, which is closest to the nucleus. You have the second, the third, the fourth, and the fifth in this model is the furthest out there. But notice how the electrons travel in these definite paths referred to as orbits. Now, a phenomenon we had talked about before was the photoelectric effect. You see, electrons, if they absorb sufficient energy, they can jump from an energy level to a higher energy level. The normal location of an electron we know is known as the ground state. And if an electron receives sufficient energy, it can jump to a higher energy level, and it is known as an excited electron. Well, you're going to see that these are line spectrums. They're actually produced when the atoms are ionized and they are given energy, and the electrons get excited, they go to a higher energy level, but these line spectrums are produced when the electrons drop from a higher energy orbit to a lower energy orbit. As they are moving back down, whatever energy they absorb, they will release. Now, since atoms are all different, they absorb and release different amounts of energies, and that is why each element produces its own line spectrum. You can see below here that the line spectrum is a spectrum that contains only certain colors or wavelengths depending on the atom that is being utilized. There are three examples here. You could see the hydrogen line spectrum. There's very few lines, and that is hydrogen only has one electron, so it produces very few lines. Then you got helium, which has a few more. Helium has 2 electrons. And then you got neon on the bottom, which produces many, many lines. Okay? We're going to focus on hydrogen for a moment, since it's the most simplistic one, but every single element has a unique line spectrum. You can think of the line spectrum as the fingerprint of the element. Well, here is how these lines are produced. As you can see, when an electron gets excited, which is referred to as excitation, it's absorbing energy. The energy, as you can see, is coming in there. The electron jumps to a higher energy level. So this one jumps right out here. But it is when they return back that they release the energy that produces these line spectrums. So notice it's referred to as relaxation. You see the electron is emitting or releasing energy as it falls back down to the ground state, or as it's going from a higher energy level back to a lower energy level. This is the line spectrum of hydrogen. Notice the hydrogen spectrum has a series of lines divided into 3 sets. There is a set of lines in the UV region which the human eye cannot see, and we know the set is known as the Lyman series. The only ones that are visible to us, which will produce various colors ranging from violet to red, is the Balmer series, and the Balmer series is the sets of lines produced in the visible region of the spectrum. And then we have a few lines in the infrared region. Again, humans cannot see this part of the spectrum. And this set of lines is known as the Paschen series. So why so many lines? Well, this is the answer. This is hydrogen, and potentially there are 7 energy levels. So every possibility is shown here. See, an electron, if you notice the Lyman series, which are represented with the purple for ultraviolet, notice that they release the most amount of energy. So you have a line that can be produced when the electron goes from the 7th energy level to the 1st, from the 6th to the 1st, from the 5th to the 1st, and so on. In the visible region, you have a medium amount of energy released, okay? And I know the picture here doesn't really show the accurate description, and you'll notice that there are 4 lines that are produced in the visible region. One is in the red area, one is in the greenish area, bluish, and violet area. This is, all of these, or at least these 4 lines, are in the Balmer series, which is in the visible portion of the spectrum. And then there's a few that lines are generated in the infrared region, which is the Paschen series. These don't release as much energy as the other 2 series. But the reason hydrogen produces so many lines is because of each line in this picture represents a possibility of an electron dropping from one energy level to another. Now, the problem with the Bohr model is that it only works for hydrogen. What good is a model that only works for one element and doesn't work for the rest? So, a second and more modern model is known as the quantum mechanical model of the atom. Erwin Schrödinger proposed that atoms do not travel in orbits. Instead, atoms travel in something called orbitals. So let's look at what an orbital is. An orbital, basically, I want you to think of it as a region. It's defined by an area, okay, like a room. So think of an atomic orbital as a region around the nucleus where the atom has the highest probability of being found in. So think of it as a room that if you look in that room, there's a high probability of finding the electron in that room. So it all has to do with probabilities. Now, these rooms, you will see, have shapes, okay? There are different types of orbitals. In another video, we'll learn that there's an s orbital, a p orbital, a d, and an f, and each of these orbitals has a specific shape. So think of orbitals, you can think of them as clouds showing the region of probable electron locations. Now, there is a term I want you to differentiate, and that's called electron density, which is has to do with the density of the electron cloud. So if you have a region where the electron is most likely to be found, where the probability is high, those regions are referred to as regions with high electron density. That usually would be electrons in their ground state. However, electrons can, if they absorb enough energy, leave the ground state, go to a higher energy level, and regions where you will find the electron with a lower probability, those regions are said to have low electron density. Okay? So the one thing that does happen is when electrons get excited, eventually they always will return to their ground state. So that's the difference between high versus low electron density. Again, high electron density is regions that have a high probability of finding the electron. Regions of low electron density are regions where the probability of finding electrons are low. So let's take a look at the difference here. According to Bohr, let's say this is the nucleus, and here you have an electron. Bohr says that the electron always travels in the same Bohrian path, in a definite path. It doesn't deviate. It always travels in the same path. Okay, that is how Bohr describes, his model. Now, Schrödinger says that instead, okay, and we're looking here, this is the Bohr diagram. So with Schrödinger, let's draw the same thing. Here's the nucleus. But Schrödinger says that instead, an orbital, okay, we'll put here orbital for Schrödinger. Let me write this down. Okay, so for Schrödinger, let me get, the spelling. Okay, let me get that fixed. There we go. So for Schrödinger, here's the electron. The electron does not travel in a definite path. Think of an orbital as a region, and this is the boundary. Think of this as being a room. And if you look in that room, there's an electron. There's a high probability of finding an electron. So instead of the electron always traveling in the same path, the electron can go this way, come back in here, go out, come back, like this. And it's just traveling randomly within that room. Okay? It doesn't have to travel in a definite path. Again, the electron is in this region and is just moving around the nucleus, but it does not travel in a definite path. Again, if the electron receives enough energy, it can leave this orbital and go to a higher energy orbital and become excited. So that's a major difference between an orbit by Bohr and an orbital by Schrödinger. Now, there's two other principles before we get to the quantum mechanical model. Heisenberg was a scientist who came up with the uncertainty principle. And this principle states that it is not possible to measure both the velocity or the momentum of an electron and its position simultaneously. So once you try to measure the position of an electron, it has already moved somewhere else. It's impossible to calculate the two of them at the same time. And because that cannot be done simultaneously, it's known as the uncertainty principle by Heisenberg. Okay? And then one more principle, as we get closer to this new model by Erwin Schrödinger, has to do with Louis de Broglie. What happened was, if you recall, when we learned about light, we learned that light is both a wave and a particle. Well, when we learned about electrons, we always think of electrons as particles. In fact, we think of them as negatively charged particles. Well, what happened is that de Broglie proposed and was able to figure out that electrons are just like light. See, he proposed that electrons might also have wave-particle nature or wave-like properties. So if the electron is like light, then not only is it a negatively charged particle, it also has wave-like properties such as wavelength, frequency, crest, trough, all the properties that waves exhibit. So what ended up happening is that Louis de Broglie proposed the idea that electrons also are waves and particles, so they're both. Now, look how important this was. Once Schrödinger realized that electrons also had wave-like properties, he began to devise equations by treating the electrons moving around the nucleus as waves. Okay, now you know in math, we have equations. And when equations are graphed, they give you a shape. We have an equation, like a quadratic equation that gives you a parabola. We have other equations that give you a circle. So equations, when graphed, can give you a shape. So Schrödinger's wave equation, so that you know, it's a mathematical model. And the cool thing about this model is that it applies to all atoms. Keep in mind that the Bohr model was accurate, but it only worked for hydrogen. Like I mentioned before, what good is a model that only works for one element and doesn't work for every other element? Well, what we're going to call the quantum mechanical model proposed by Schrödinger, it works for all the atoms. So Schrödinger's wave equation is going to lay the foundation for something called modern quantum theory. And what quantum theory does is that it describes mathematically the wave properties of electrons as well as other very small properties. Now, we're going to focus on electrons, okay? Because what's going to happen is Schrödinger is going to treat these electrons as waves. He's going to devise equations, And the neat thing about all of this is that when Schrödinger's equations are graphed, they're going to give you these specific shapes. It happens that those shapes are the shapes of the orbitals. In another video, we're going to see these equations and we're going to see the shapes of the orbitals. I mentioned before, there are the four main types is the s orbital, the p orbital, the d, and the f. And the shapes of these orbitals have to do with the mathematical equations that Schrödinger devised by treating the electrons as waves. So the model that we're going to be looking at is going to be known as the quantum mechanical model. We're going to be talking about quantum theory in the next video, and we're going to see that that's divided into something called the quantum numbers. So the Bohr model, which only works for hydrogen, that one, it has its obviously its limitations. The new model that represents the atom that right now, as of today, is the quantum mechanical model.